Yeah, so let's start. So first we'll look at the video of what happened that day, and then we.
Always a good idea to move.
Slides not good. In our case it worked, but when you heard of it,
Yeah, that's why you should transfer it again. Anyway, continue. If it doesn't play, it doesn't play. We don't waste time. Move on.
It was a typical constructed shooter morning at Cape Cod. Here are the last seconds of the countdown. 3, 2, 1, and liftoff. All communications between the shuttle and mission control indicated everything was going fine. There was a sense of relief that the Russian spacecraft was finally on the way. It happened just over 1 minute into flight.
So what we want you to focus on is that until it was looking very fine until this tragedy occurred, and we will look at what happened that day. So what is our objective in today's presentation is we'll discuss what was the Challenger mission, what made the mission so special. The mission name was STS-51L, and what were the events that led up to this disaster, and the infamous day that happened, the tragedy, how did the shuttle function, what findings did we find, and then what were the causes of it, and what were the environmental factors, and how did we improve it later on. So what was the Challenger mission? So the Challenger shuttle was originally intended to be a test vehicle, but then they later on, but NASA later on converted it into an operational orbital. So it was very pivotal in scientific experiments throughout NASA's first 25 flights, and compared to its predecessor Columbia, the main improvement was it had a lighter airframe made up of lithium aluminum alloys, and it had an improved thermal protection because it was made of the heat resistant tiles were made of ceramics, and there were upgraded avionics through a lot of different areas. Now, what made the STS-51L so special was that NASA introduced the first teacher in space program. This mission was intended to introduce space to young kids, and that is where they sent a teacher named Krista McCauley, and the main objective of the mission, the scientific objective of the mission was that they wanted to deploy the TDRSP, the tracking and data relay satellite, to improve NASA's data relay capabilities, and also they wanted to go to the Halley's Comet, collect data from there, and then process it on Earth. And there were multiple experiments like fluid mechanics and other things performed. But however, as we know, this never happened.
flight takes off with a thrust more than the gravitational force which was impeding it. So first of all, they decided like in 1985 that they would be launched on January 23rd, 1986. But due to payload issues and the weather, they had to postpone this, and there would be some more issues which would come up in later. That was the first one. Modern Global, which was the contractor responsible for making these SRBs, they want NASA that they can have O-ring failures. They also asked they wanted lighter steel frames for the rocket boosters through which they would made. Now the thing was, these O-rings were used for consecutive. This was the 10th Challenger flight, and 25th of the last which was going to go, but NASA said there have been no flight tragedies so far, so why can't? So we moved on to January 1986. So there were the westerly winds in Florida that time. Kennedy Space Center was the launch location. So isotopes would have found because they were on the other side. There was no sunlight, and what we faced up was isotopes coming onto the surface of the rocket boosters, like at the very end. The Challenger was supposed to launch on January 1986, which it did at 11:38, achieved liftoff, and then so now the remaining sequence is to tell, but we can't cover all of them right now. We'll cover them bit by bit when we reach to the materials. So at t 58 seconds, that is 58 seconds after the liftoff, it's 11:39. A plume of flame appeared from the right side rocket booster. As you would have seen in the video, there was slight black smoke which is called the bird by. So what exactly happened? That that black smoke went off. But after 58 seconds, a very large flame came up, and it was assumed that okay, the failure was one of the O-ring seals. At t was 1:13 seconds, the Challenger disintegrated due to the structural failure of O-rings, and the more important thing which I covered later. And at t was 1:14 seconds, the last signal from Challenger was received. Okay. So, first of all, we will talk about the working of a space shuttle. I can skip this because I would like to go on to the next slide and explain how exactly Challenger works. So, first of all,
there should be a pointer there, not stick point, please, sir.
Do we have?
I have it's ready.
Okay.
Stick point, yeah.
So, as you can see, this is how a space shuttle is generated. We have main engines which will propel, like they are not the entire journey which is presented to us. We have this orbiter. Our orbiter here was Challenger. Challenger was one on the mission C61L, and it was on SPO099 if you would have seen that. Now we have two solid rocket boosters here. These are for the initial thrust which are provided. This is the payload bay, and they have a fuselage. Like so, a payload bay is whatever is needed for the equipment and whatever you need to take it for the flight. You have the system, the irrigation systems, and lots of electrical equipment there. There is a fuselage which connects this, and there are two shafts which connect the external tank which has liquid hydrogen in it, which provides fuel to the solid rocket boosters through a joint. Now, if I come back here, so how the rubber domain looks, I'll explain this in a while because this has some more technicalities which requires the clip joints to describe this. So this is how exactly it looks like. Now here what you see is a joint. It's not very clear, but if I have to explain, there are insulations, inhibitors, and through this you have a sufficient amount of, two O-rings, a primary and a secondary O-ring. Mehul, could you go back to the previous slide? Okay, so I will explain this. Now, if I move, the disaster occurred into the failure of an O-ring seal on the right sound. So, there was only one culprit, which was like the O-ring seals. So, one of why that happened, this was that data. The unusually cold temperatures on the non-stick caused the O-rings to lose their flexibility. It was due to because it went into the glass transition regime. And so it disintegrated after 76 minutes after liftoff. But the interesting point was to come later why it took 73 seconds and it did not explode in the very first second of the liftoff. Okay.
Yeah, so what were the first seconds? So, as you could have watched the video, what happened was that at the very initial liftoff, we saw that there was a black smoke, which was like very rarely visible if you would have seen. But the issue at that time at the liftoff was that the pressure was higher in the right SRB. But as the mission progressed, we saw that at 58.788 seconds, the pressure in the right SRB was 11.8 psi lower than the left SRB. What this meant was that there was a leak at the right booster because at the initial stage, when there was a higher pressure at the right SRB, the crew did not really take a note of it because it was in the permissible limit. But when this time occurred, the pressure was significantly lower at the liftoff compared to the liftoff. So this discrepancy indicated that there was a leak at the right SRB, and what this meant was that it totally compromised the SRB's integrity, and we saw that due to the pressure anomaly, nobody noticed how this went off and then the whole thing blew off. Now I'll
Yeah. So before I come to the O-rings, it's necessary for me to explain why O-rings are the culprit here. So what exactly ended up happening that the O-ring is an initial black smoke which is generated when so the thing is before the assembly there has to be some sort of compression in the process due to which this entire O-ring gets compressed. For that the concept of recovery is applied, which will be seen again later. Now the thing is on such cold days recovery is not so easily possible. Even in general it takes some time to recover. Some fuel passes out and we get some black smoke which is burning. Now what exactly ended up happening here was I will show you through this. We have this AFT facing inhibitor and this is the zinc chromate putty put with asbestos.
Use the pointer.
So we have this zinc chromate putty with asbestos put in here. This is an entire installation here where it also has asbestos here. So there are two pinnings which hold the O-rings together here. One is the crevice pin and one is a cement tap. This is called the tank crevice joint. With the tank crevice joint, we can put the O-rings in place. Now the thing is, O-rings are made of it will be covered in a way by F-paints, which is some fluoroelastomers. Now what happens is at very high temperatures, the temperatures which we be seeing in here are temperatures of around 32 degrees Celsius. These are the combustion gases which we look at. What ends up happening to this is it will easily burn up. Even though they have high temperature resistance, they will burn. So what we do is we put an inhibitor an insulator on. Now, so what exactly happened with these O-rings was that they were the culprits. So they were supposed to be elastic sleeves which would prevent. I'm really sorry, but I forgot to mention this. The insulators are used for thermal resistance and the O-rings are used for pressure resistance. I will show that in the next slide. We will go on to the next slide before the experience. So I can see in here what exactly is happening is, so we are throwing out the liquids and the gases. The O-rings, now if you go back to the previous slide. So what the O-rings here do is that they connect the ignition chamber that is from the external fuel tank and the solid propellant systems. So the propellant here will do a very important thing because propellants have aluminium, which will be a funnily interesting thing to see. It's sarcastically speaking. What exactly is happening is, so when you put, so O-rings are used to moderate the stresses which are required due to the passing of liquids or gases. When we go through the primary, it will apply some stresses, and due to that it will be compressed. It will try to fill into the gap. These gaps have some certain abilities which will also play an instrumental role into understanding why exactly these gaps are important. We'll see later how larger gap sizes will be more useful in making better O-rings. So this goes in, and the thing is, O-ring, the material used for O-ring here have very high. We choose some materials which have very high surface tensions. So we could go on to the next slide and begin from there. No. there is a lot of compression happening in these regions. So what it will try to do is force the O-ring into this gap. Now what exactly happens if we put the O-ring into this gap? This has some force tension. Now if the stresses would most probably forces applied by this region, using this curve region, the surface tension, it will try to overcome it and go all the way. So this is how you modulate the gases or the liquids to flow from one chamber to the other chamber. So what was the main issue? I would say everything went wrong on this day. So what happened was that the temperature of the Kennedy Space Center dropped to 36 degrees Fahrenheit. This is the operational temperatures which we can allow permissible limits of 41 degrees Fahrenheit. But it was down to 36 degrees Fahrenheit. And the O-rings were made of FKMs, we'll discuss again later, have a glass of transition temperature between minus 10 degrees Fahrenheit and 5 degrees Fahrenheit, which is depending upon the material you choose. Now, temperatures, even at the launch, by the time the morning it was cold, it went down to 29 degrees Fahrenheit, which is still under the working limit, which is below the working limit, so we can't use it. Why exactly? So, it is because of the local brittle and local elastic behavior which was formed at the due to the glass transition. So some parts have become more brittle and would crack more easily under stresses. So the cold was the primary O-ring of the Savi's FT going to like space and expand very quickly. And because due to this, what had happened that from the FT joint where the gases came, they had a lot of time to put pressure on the insulator because which the insulator did not work and the O-rings went all the way to be destroyed because they were already brittle. And they had a, because of the joint flexing not working too well, they were destroyed. So the seal went off and the hot gases went and ignited the external fuel tank. There is something which happens in between which I will cover in a while. So now any of the launches before this were not colder than 53 degrees Fahrenheit. And the thing is, when we are talking about this was actually the previous year before this, and it was STS 52C. And in that 53 Fahrenheit, one of the primary rings went off. They somehow managed to survive with just the secondary rings. If that would not have taken place, we would have had a worse casualty. So, not many options. Now, we need to go that. So, the thing is, when Martin came to know that the primary and the secondary O-rings have a lot of bearing because the time machines which have happened, this is so good at that point of time. They were okay. Now all the machines are now going to come and they will pass into the external fuel tank and burst it. That is what they expected. It should happen within a second. That's what they thought. But the issue was it took 73 seconds. And the reason for this was the propellant. The propellant had aluminum. Now what happens when the propellant fires up? It uses a lot of oxygen. In the process, it forms aluminum oxide, which acts as which can be corrected one half. Yeah. So here the propellant would go all the way and put a very small ceramic plate of aluminum oxide. Now the good thing about aluminum oxide here is that it would resist for a while because it has a melting point of 3700 degrees Celsius. It is also to some extent chemically resistant, so it will work very well for 73 seconds. But then again, what was the issue? We'll see that later. But before that,
Yes. Now coming to, we are talking about O-rings. So what are they made of? So they were made of FKMs, and FKMs is a synthetic rubber composed of fluorinated hydrocarbons, and they are known for chemical resistance, thermal stability, and also they are like really tough. The main reason NASA chose FKMs were because of their toughness. Higher the toughness, higher the energy, so higher the strain energy. So now the choice of FKM for the O-rings in the SRT was primarily due to these factors, because these are the main factors that a rocket encounters. These are the main reasons it can fail. So FKM can withstand very high temperatures and very high pressures. But what happened on that day was that there were very low temperatures, and that was the reason of the failure. I'll go to that. So as written here that FKM excels at high heat conditions, but the main issue arises when the flexibility and sealing properties nebulation at low temperature. This was due to the partial transition to the glassy regime. As the temperatures drop, the relaxation time increases, and because of the relaxation time increase, the local stresses are increased. So because of that, fracture can occur. So on that day, especially, the temperature was so low that we entered into a partial rubbery and partial glassy regime, and that is where FKMs on that day failed to stop the fuel from, as we saw that it would stop the fuel from going into the other chamber, but that day it just completely fractured. Yeah, and now I'll talk about recovery time. So what happens is that as higher temperatures, at higher temperatures the recovery time is pretty low, but at lower temperatures the recovery time is higher. As I said. Yeah, so as you can see that at lower temperatures the recovery rate is even lower, because of whatever I said before. The relaxation time is so high at lower temperatures that the recovery rate that is there is very low, and that is what NASA eventually figured out for FKMs, for the O-ring, that at different temperatures they saw the recovery rate, and at higher temperatures the recovery rate was higher, at lower temperatures the recovery rate was very low because of the relaxation time. Yeah. So what happened after this was President Reagan appointed Rogers Commission, and the main things, the main culprits were NASA and modern cycles, faulty engineering, and the main thing that happened was
Wrap it up in 2-3 minutes.
okay. So modern cycle was very business minded, and they really modern cycle and NASA, they were really running short on time, and they wanted to do it as soon as possible. The absolute joint failure in the right SRT was due to a faulty design, and it was the primary cause of the disaster. So eventually we did redesign, and NASA completely reworked the system with stricter protocols for safety. So now were there any other factors?
Yeah, so we come to more important factors which were caused by the environment. First one was the wind shear. So like our atmosphere, which we say troposphere is very stable, but as we move up, the dynamics are very different, and wind currents will be very local, which have their own gradients associated. So the thing was, this wind shear started at 37 seconds and went all the way to 64 seconds. And later this, we had a lot of added stresses which were already on the compromised domains into the right side rocket. So this was now applied on the 8th core filter. And then the more important thing was the overuse. Overuse came from they had a lot of equipment which had already been doing this one for the last periods of time, and 9 times they had not changed anything. So overuse was one of the bigger reasons for by nothing over here. And lastly, the aerodynamic resistance was a very big factor. So as Mehul would have mentioned, at the very end, the left rocket boosters had a lot more pressure than the right rocket boosters. So what happened was, the left rocket boosters tilted it towards their side, and the right rocket booster did towards more forces at the faulty engineering from the EFT junction. It started to throw out gases, and so the right rocket booster started to spindle up and down. Ended up happening what is due to this, the aerodynamic resistance was also at its peak. It started at around the same time, and by 45 seconds, NASA had come to know that they are in a CV double duty columns. So the mechanism is
Try to wrap it up in a minute or so.
Just a minute. So we have gotten local brittle behavior which we have discussed, material stuffing of local brittleness, and gas leakage, thermal degradation, and chain reaction which happened in all that part. So NASA posted all its launches. So what did we get? So we got two things. First was discovery. Discovery was also launched in 1985, but had come part down to 1988 because there was a lot of fuss to see what this video was for. There was a major discovery Rogers Commission. They had done that. The replacement for Challenger was made, which was Discovery, and that launched as STS-49, using all the advanced systems like radio and GPS, and then all navigation systems, and served it to 111. So it was made for Clovis Airports. We have the references there, and thank you.
couple of questions from the audience. Just raise your hand and I'll call upon you. I encourage participation. You'll be given marks for that as well. So,
Yes, sir.
No,
please raise your hand.
Students.
Students.
Because mine really belong.
Wait. Students. I'll call
Yeah,
on
I
you.
the students.
Any questions from the audience? You will be given credit for participation. You will be given marks for that.
Since we're dealing with
Please raise your hand. I'll call upon you. Yeah. Come on.
because we're dealing with the rocket, we also need to take into consideration that there's a decrease in temperature for every 1.6 meter right? So with the failure analysis, I was taking into consideration the action setting that we are 87 seconds space directly or correct temperature.
Yeah, good. So first of all, I would like to tell you this. When you talk about that linear degrees of the temperature, that's first of all a very standard approximation. Temperature is not very like that. It is just because of the pressure degrees we make all those functions. They are for the ground truths. Now, secondly, like you would have seen, like even in ISS, you have temperatures like 200 degrees Celsius. If you would have seen. So temperature is not like that. And we had, if you would have seen, we had heat resistance in our planets. So we don't have any issue at least on. Below that, we have metals. It's made of aluminum and lithium alloys, solid rocket boosters, steels, which do not face such big issues. Like the turbulence is all countered by the inner atmosphere, which is made of ceramics. So that is one thing. Apart from that, there are other things. No, let me finish one thing. So I tell you, around the solid rocket boosters, what you have is you have temperatures much higher. You don't need to think about you are going for 200 degrees Celsius. You have temperatures of 3000 degrees Celsius already moving around. It's not 3000, but something around 3000. So you don't need to care about that. We have already talked about the kind of quite yeah, sure.
Yeah, so basically the O-rings were already surrounded by a very high temperature, so you know.
You were already on.
Yeah.
Wait. I'll call upon you. Don't come. I mean, when I raise your hand, I'll call upon you. So, yes, Shweta.
Can you tell in one sentence that why it took some 70 seconds or time to rise?
Yeah, I'll explain. So what happened is that initially you saw a black smoke. So Alan McDonald, the representative of modern arrival, said that in the first few seconds, in the first 1/10 of a second, if the rocket had to fail, it would have failed in the first 1/10 of a second, but it did not. What happened was that they already predicted that the O-rings would fail because of the cold weather, because of the brittle nature of O-rings. They would just completely fracture because of, let's say you have, these were the O-rings and these were very brittle. These were very brittle, right? And as the temperature increased due to the influx of the liquid oxygen that was like very high temperature gas, it completely ruptured off, and because it ruptured off, there was no steam at all. So now what caused the delay? What caused the delay was, as we know, the propellant was made of aluminum. So the propellant had aluminum. So aluminum came in.
Mehul, he said briefly.
Sorry. So basically aluminum created a brittle. It created a brittle seal which eventually fractured off because of the high temperatures. Basically, and then
That's fine. We have to keep time in mind. Anybody else? Yeah.
First, I think I made you nervous. I want to say it was a nice presentation. It's also interesting for me. The tragedy after this, I lived in Texas when that happened, like blinding on me. Anyway, I wanted to motivate our lab actually with this. I think we can come back to our constant strain rate labs maybe sometime, especially. And I wish I'd done the nylon better for you guys. And I'm curious, you could think I'd like to see this dust rate curve for this FKM, know its price. PDMS might be better. I don't know if you've done these before fail. They've done all that before?
I don't know.
So I looked into alternatives for FKMs because they are cheap. They were PDMs, nitrile and silicone. So they are like the newest ones which we use in the polymers. That is what I came to know. I think nitrile is the cheaper, the most cheaper.
I tried, I said, so I was, yes, I captured too much. I did something I would have given you as a comment, I spoke fast. Maybe because there were several questions I wanted to ask, but mainly I felt the labs you just did with me and Dr. Malay, many of them apply here. The fatigue lab, we kept talking about it being used before, stress rate, this flow of this, so the alumni is right, it's brittle. What about this NKM? It's not brittle, it's viscoelastic. In specific, it's an elastomer, right? And then what about this you haven't done yet, or maybe you have entropic spring? Yes.
This is equal to T minus T.
Yes.
We have to keep the same short.
Yeah,
We're already running
it's
a
on
short
time,
time.
but nice presentation, and maybe we can get you all excited about the labs. So, yeah.
Okay. I have a couple of, wait. I have a couple of, come on. I have a couple of questions. I'll direct it to individual people, okay? Don't cross answer. Please, don't answer for the other person. You guys said so much about the O-ring material, but what is the TG? It was never mentioned anywhere. Mehul, I said I'll call upon people. Yeah. What is the TG for this elastomer?
So it was about 5 degrees Fahrenheit. So what exactly is your question?
That was the question. It was never mentioned in your presentation.
No, it was mentioned. The glass transition temperature for that was about 5 degrees Fahrenheit.
So
Okay.
I think the point is, it's the highlight of your main key.
This entire thing, this is for other groups also, this is about materials. The focus should be on the materials aspect, not the other stuff. Other stuff is incidental, focus on the material side of the process, okay? But can I please? If it is 5 degrees Fahrenheit, that particular day was the O-ring above TG or below TG?
It was above TG, but what happened that was there were local stresses. So it was not totally in the glassy regime, it was partially rubbery and partially glassy because of the local.
Okay, fine. You also mentioned that liquid oxygen coming in at high temperature.
So like basically gases coming in at high temperatures would basically like liquid oxygen at
Liquid oxygen is high temperature.
sorry they were basically gases that would combine.
Again, for you, or maybe I can ask Mike. You mentioned recovery several times, but what is recovery? I don't understand what it means.
Yeah, so first of all, recovery is a time-based function concept. And what
No, I saw the equation, but what does it mean? What is the implication? And what was that evolution with time?
Yeah, so first of all, recovery simply tells how easily the dimensions recover over with time. Like we have seen in creep or time-dependent plasticity takes place, and we are talking about more of time-dependent elasticity or easily do the
Correct, but what do you mean by recovery? I want a definition of that.
recovery.
You keep saying about recovery. What do you mean by recovery? I want a definition of that.
So
Can I?
No.
Yes.
So recovery is an elastic. Recovery is a mechanical property of a material to retract back to its original shape in a given amount of time. Like the percentage of recovery simply tells the amount of energy it has taken.
Energy.
Yeah, like it has to go back from the compressor state to back its original state. So how much can it work back to its elasticity?
You said something about when the temperature drops, the relaxation time increases.
Yeah.
What does that mean?
So
What relaxation time is this?
So basically we are talking about how exactly we studied TG in general. So the relaxation time means if I put them under some stresses and let it go on, we will have some sort of it will try to recover back into its full state. So at every single point of time I measure what the dimensions are with respect to their original dimensions.
No. I'm asking about relaxation time. I'm not talking about recovery.
Yes. So
Answer that question. Temperature drop leads to an increase in relaxation time. What does that
yes,
mean?
so since the recovery rate is slower, we have a larger time for it to recover into its 100%.
Can
That's
I
all.
ask them something related?
We don't have a lot of time. We have to keep technical content short. Okay, so just these are comments, not questions. Focus on materials. Material focus was not there. Okay. The important things that you need to show are the elastic modulus versus temperature curve for this material, which was not there. The recovery, the relaxation curves. stress relaxation curves, which are not there. Nothing about the materials was covered. Right? These are comments. I'm not asking you to say anything. Okay, these are comments. So focus. This is a materials course, so you should focus on the material side of the thing. And in terms of improvements on the material side, what was done? What was the change to the boring materials? All that is important. Okay. And in terms of the presentation itself, Mayank, you need to slow down, speak with clarity. Your words are garbled. I can't understand 80% of what you're saying. It helps to prepare what you want to say, and it helps to speak slowly and clearly. Okay. So that's all I have. Thanks for the effort that you guys put in. So let's give a round. And please wrap up your presentations after I say 2-3 minutes. Wrap it up at that point. Okay. So the next group is going to be the D. Have you any comment? Please get started.
Can you check that ours is there? Like you said that one of the.
I have my laptop there. I don't know which one.
Just can you?
I can't do now.
No, Colombo is there.
I can't do now.